Okay, welcome back. We are going to start today with fluid statics. So, in the last lecture, I exposed you to the idea of a stress on a fluid, right. So, when a fluid moves, then it leads to certain surface forces, and we talked about what happens to the state of stress. Now, we take a special case where the fluid is stationary. Okay. So, that means what this implies is that by its very definition, because the fluid is stationary, it means there is no shear force. So, recall, fluid starts moving due to shear force. So, that means if I look at fluid which is stationary, then I can only have a normal stress. There cannot be a shear stress. Let us call this pressure. And now I want to find out what happens to this pressure in this scenario. So, let us consider, so let us say this is the free surface of the fluid, and there is a fluid inside, and I am going to write down a frame of reference. So, this is x and this is z, and now what I am going to do is take an element of fluid in this. So, this is the element of fluid. Let me say this length is delta x and this height is delta z. Rho is the density of fluid. Let us say there is a pressure on this which I called as Pn, and there is a pressure here which I called Px, and on this face the pressure is Py. So, of course, these are distributed pressure, but I have just shown you with one arrow not to clutter this diagram. This is also going to have a weight. So, let me draw the weight of this fluid element. So, it is going to act through this point, and I could say that suppose L is the depth of the element inside the board. So, I am going to consider an element of depth L inside the blackboard. Then I could say the volume, the delta volume is delta x times delta z times L. And therefore, this force I could write down, the weight is simply rho times delta v and g. Okay. Let me call this as an angle theta. Okay. So, I am primarily interested in what happens to the value of the pressure on this normal surface of this wedge. So, let me do a force balance. So, x balance, and I will do a z balance. So, there is a force in this direction which is minus Px times the area, and the area would be simply delta Z times L. So that's the force in the negative x direction. The force in the positive x direction is because of this Pn. So I'm going to write this as plus Pn times, suppose I call this length as delta L. So this would be Pn times delta L times this L, and I am going to take the component of this. So this is theta, which means this is theta. So I am talking about L sine theta, and this is 0. So I have taken this force and the component of it in the x direction. All right, I can do a similar balance for the z direction, which is the vertical direction. So there is a force, a pressure acting on this force on this face, and that value is in the positive direction. So I am going to have plus Py times delta x times L, and then I have the weight. So that's in the negative direction. So that's minus rho delta x delta z by 2. So that's actually the volume times L and a g in this. And then I would have to take the vertical component of this, which is again in the negative direction. So that would be minus Pn times delta L times L. So I am sorry, this should be a small lowercase l, and of course a cosine theta. So this should be 0. So let me call this as equation 1 and this as equation 2. Okay. All right, what does equation 1 give me? So equation 1 implies that, maybe I will get rid of this, and I see minus Px delta z plus Pn, there is a delta L, and for the sine theta I can write down this is delta z by delta L equal to 0. So these cancel out, and this implies I have Pn equal to Px. Okay. Let's see what the equation 2 gives me. Equation 2 tells me that I have Py times delta x. So I am already going to cancel out this L, and minus rho delta x delta z by 2 g, that is the second term, and then the last term is minus Pn delta L, and cosine theta from this triangle I could write as delta x by delta L. This is 0. So I could cancel out these delta L's. Similarly, I could cancel out the delta x here, 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 and therefore I get Py minus Pn is equal to rho delta z g by 2. Now if I take an infinitesimal element, so limit delta x delta z tends to 0 on this equation, then I get Py is equal to Pn. That means if I look at this fluid element, then these two pressure Px and Py, they are both equal to Pn, and therefore they also must be equal, and that is the famous Pascal's result. So essentially, let me summarize this for you. So this is the result due to Pascal, which you have already looked at in your high school, and it says that in a stationary fluid, pressure is same in all directions. In other words, we could also say this is isotropic. So pressure is a very special quantity. So if I take a small fluid element, then pressure on all these faces are going to be equal. So that's a very important result. Please note that we have not proved this result for a fluid that is moving, okay, or which has different speeds at different points in time. So this result we have shown is proven only for a stationary fluid, but of course we know that this result is true for other situations also where the fluid is moving. Good. Now what I want to do next is, having shown that pressure is same in all directions, I want to find out what is the variation of pressure going to do. So suppose I have pressure that varies from one point in the fluid to the other, then what is the implication of that on the force that acts on the fluid? So we are going to talk about the pressure force on a fluid element. So I am going to set up a coordinate system and then consider a fluid element. So let me set up a coordinate system for you. So again we will take a right hand coordinate system. So let us say this is x, and so maybe I should this is z, x, y and z. And let me consider a fluid element. This is a fluid element. So this is the positive x phase, and at the back of it I see a negative x phase. Similarly, I have a positive y phase over here and a corresponding negative y phase, and so on. So I am going to allow pressure to vary with x, y and z. So I am going to say that pressure is actually a function of x, y and z. It could vary. All right. So suppose I look at the pressure at this point and I look at the pressure at this point, and the only difference between these 2 points are that they have different x, but y and z are the same. So I am going to assume that pressure on this face, which is normal to this face, is P. But on this face, the pressure is P plus del P by del x times dx, where this length is dx. Similarly, I could talk about a pressure on this face over here, and I could talk about a pressure on this face. In fact, I have made an error in the direction. As I showed you, pressure is inward, so this pressure should be like this, and I am sorry, this pressure should be inward. Pressure acts on the surface. Okay. So this pressure would be P, and this one I would like to call this as P plus del P by del y times dy, where this length is dy. Okay. And likewise I could do for the z direction. which is of course in this direction, but I will not clutter the figure. Okay. So, I could talk about the net pressure in x direction on this fluid element. So, please notice, because pressure acts normal to the surface, so in the x direction only these two faces contribute, no other face would contribute. Similarly, in the y direction only these two faces would contribute and not the other faces, and likewise for the z direction. So, as far as the x direction is concerned, I would only like to take resultant over here, and I could write this as P plus delta P by del x times dx. So, there is a negative sign here because it is acting in the negative x direction, times the area over here. So, I would like to call this as dz. So, this would become the area, as you can see, is of this face is dz times dy. And then I have pressure on this face, and that is in the positive direction. So, I have plus P, and now this is dy dz. Okay. So, therefore, the net pressure that I have is these two terms will cancel out, and I am going to be left with minus del P by del x dx dy dz. This is the net pressure force in the x direction. Likewise, I could find out what happens in the other directions. So, net force in, for example, the y direction, and that would be given as, I could again del P by del y dx dy dz. In fact, we could already see that from here. So, if I compute the force because of this pressure over here, so it is this pressure times the area, and the area is dx times dz, right. And then I have another force because of this blue colored pressure on the lower surface. So, part of it is going to cancel it out, and the remaining one I have written over here. Similarly, in z direction, this is going to be equal to minus del P by del z dx dy dz. Okay. So, I have been now able to find out that on this fluid element, if there is a pressure that actually varies spatially, so it is varying at different points in the fluid, then what is it that leads to a force on a certain fluid element. Okay. So, these are the three directions. So, now I can write it down in terms of a vector. So, I could say that d Fp is the net force on the fluid element due to pressure, and this I could write it as, in the vector notation, minus del P by del x I, that is in the x direction from here. Similarly, del P by del y in the j direction, and del P by del z in the k direction, times this dx dy dz. Okay. I could in fact write it as minus gradient of p dx dy dz. Okay. So, this is a very compact notation where I have already shown you what is meant by the gradient operator. So, it has 3 components which are listed over here. But this must be balanced. If it is not balanced, then it would cause this fluid element to move. Okay. So, suppose I have gravity. So, if I now write down dFp as the pressure force per unit volume, then that is given as minus gradient of P, and I can get rid of this quantity here, which is essentially the volume of the element. All right. Next, what I can do is I can try to find out, do a force balance between, so observation 1. Net force depends on pressure gradient and not the pressure. Okay. So, this is a very important result, that the absolute value of the pressure is not so important. It is actually how the pressure is changing in the fluid that is more important. So, often we have this concept of absolute versus gauge pressure. So, if P is my absolute pressure, then I am going to define P gauge as P minus P atmosphere. This is the atmospheric pressure. So, often when you do fluid mechanics, then you would be interested more in the gauge pressure and not the absolute pressure. In fact, it is very interesting to note that Pg less than 0 would imply you have a vacuum, of course a partial vacuum. So, wherever you have a pressure which is lower than the atmospheric pressure, that means you have a partial vacuum. Of course, a perfect vacuum would be when your absolute pressure is 0, and that would imply that your gauge pressure is negative of the atmospheric pressure, and we all know that it is very difficult to achieve. You would have to have an absolute 0 temperature for that, and so on and so forth. So, now I would like to show you what is the basic equation for fluid statics. There is a force because of the variation of fluid pressure, and that force clearly must be balanced by gravity. So, therefore, I could write the equation as d Fp plus d Fb equal to 0. So, this is due to pressure, which in fact is a surface force, and this is due to body force, example gravity. And we already know what this is. This would be actually rho times g times the volume of a certain element. So I could now write down this equation as gradient of P, which is, I had shown you, is the force because of the pressure, and this times OG is the equation. Okay. So the force because of the pressure gradient has to be balanced by the force due to acceleration due to gravity. So this is the basic equation of fluid statics, which of course you are all familiar with. You have actually read this in your high school physics. We can now simplify this for a certain coordinate system. So suppose my coordinate system is that this is my z axis and this is my x axis, this is my y axis, then g is minus g k. And then this equation would result, so if I call this as equation A, so A would result in three scalar equations. The first equation is del P del x is 0, so there could not be a pressure variation in the x direction. Similarly, del P del y is 0, so there cannot be a pressure variation in the y direction, but there would be a pressure variation in the z direction, and that would be minus rho times g. Okay. So one can look at the forces on a body by simply integrating these three equations. So this leads to, so using these three equations, I can talk about hydrostatic pressure distribution. So imagine I have a fluid and this is the free surface. So the pressure here is P naught, and let us say this is my z direction. Notice I have inverted the z direction, and let us say I have fluids of different densities. So let us say this density is rho 1, this is rho 2, and this is rho 3. And in each of these layers, the density is constant. Okay. So now by looking at these three equations, I do not have a pressure variation in the x direction. Okay. That means the pressure at any point in the plane is going to be identical. The only variation is in the z direction. So in fact I could plot the pressure here. So if I looked at a pressure at this point, then the pressure here would be P0 plus rho 1 g z. So in this layer the pressure varies linearly. So maybe I can draw it. So if this pressure is P naught, then this pressure value is given as P naught plus rho 1 g z1 if I call this depth as z1. Similarly, I could call this depth as z2 and this one as z3. And of course, there could be more fluid below this. Now, when I come to a point in the fluid number 2, then I would have to integrate this equation, because when I integrate it, I have to account for the change in density. So the pressure would vary linearly here, and it could have a different slope. So maybe it has a slope like this. So, this pressure here at the end would be P0 plus rho 1 G Z1 plus rho 2 G Z2. When I go to this layer over here, then I would have to integrate starting from the value over here, and of course I could draw another linear variation. So, this would be the pressure here, and this value at the end would be P naught plus rho 1 G Z1 plus rho 2 G Z2 plus rho 3 G Z3. In fact, if you had a situation where the density was constantly changing, then also you could integrate this equation by appropriately taking how density changes with the height. In fact, this is what is done in atmosphere, where the density changes constantly as we increase the altitude. Okay? I would now like to show you one application of the manometer. So, we use an instrument which is called a manometer. This instrument is used to measure the differential pressure between 2 points in a fluid. So, I will show you a small setup, and then we will try to see how it can be used. So, suppose I have a bulb here. Let me call this as point A, and this is connected to a U tube. And this has a certain fluid in it. So, I am going to call this as point B, this one as point C, this as point D, and maybe this as point D, this as point E, and this as point O, which is open to the atmosphere. So, the setup is that there is a certain pressure inside this bulb, and that causes this fluid to take this kind of a position where this column E is at a higher level than B, and we are interested in finding out what is the relationship of pressure at A related to the atmospheric pressure. I am going to mark the different heights. So, let us say this height is H2. I will try to mark this as H1. This height between E and C, let us say this is H3, and this over here is H4. Let me say this is air, and this is a certain fluid of density rho 1, and this is a certain fluid of density rho 2. So, in principle I could have 3 fluids, one of density rho 1, rho 2, and then air. So, this is quite general. Now, we can use the equation of fluid statics and try to relate these different pressures. So, let us start from this point. I already know the pressure here, this is atmospheric pressure. So, I could write down what is the pressure at point E. So, the pressure at point E I can write in terms of pressure at point O, which is actually the atmospheric pressure, plus rho air times G times H4. That is the pressure over here. Notice the pressure at point B and D are same because we are going through the same fluid. Okay. I can also write down what is the pressure at point C. the pressure at point C could be written in terms of pressure at point E, this one, plus rho 2, this fluid is 2, times G times H3. I can write down the pressure at B, this point, as the pressure at point C minus rho 2 G and H2. But I could also relate it to the pressure at point A. Okay. So, please notice that pressure at point B is also equal to the pressure at point A if I come through this fluid plus rho 1 G H1. So, I have these 4 equations now, and they kind of relate the different pressures. So, I could plug in these equations in one another and finally get an answer for how the pressure are related to each other. Okay, let us do that. Okay, so we can now substitute for these different equations, and let us see. So, I have PA, this is equal to PC minus rho 1 GH1 minus rho 2 GH2. But PC I already know is this quantity over here, so let me substitute for that. So, that is going to be equal to P atmosphere plus rho air GH4 plus rho 2 GH3 minus rho 1 GH1 minus rho 2 GH2. Okay. So, this is the relationship between the pressure inside the bulb A and the atmospheric pressure. If I knew what are the densities of these different fluids, then I should be able to calculate this. I could now make some assumptions. So, I could say that this fluid rho 2 is a heavy fluid and it is much greater than rho 1 and air, rho of air. I could also assume that rho 1 is nearly equal to rho of air. Suppose I assume these. Then essentially I can neglect the pressure because of this air column and because of this air column, and then I would get a very simple result that PA is nearly equal to the atmospheric pressure and simply the difference plus rho 2. So, only these two terms survive, G times H3 minus H2. So, I can have a very nice device now. I can connect this device to any pressure that I would like to measure. I already know there is an atmospheric pressure, and the difference in the heights of the two column can actually be used to measure the pressure difference. In fact, you can see from this that if I am interested in the gauge pressure, then I can take away the atmospheric pressure, and this is simply rho 2 times G times H3 minus H2. So, now we are going to use these equations that we have studied about fluid statics to understand forces on a submerged object. Hydrostatic forces on a submerged object. We are going to assume that there is a free surface. So let's say this is the water level, and there is a certain object which is submerged in this fluid, and we are interested in calculating the force on it. So we can put the axis. So let's say this is the z axis, and maybe I can call this as the x axis. In fact, if this is the atmospheric pressure, then it's easy to see that if I wanted to plot the variation of pressure, then if this is the atmospheric pressure, then I am going to get a linearly increasing pressure, and P would at any point would be given as P atmosphere minus rho g z. Notice z is increasing in this, z is positive in the upward direction, and therefore I have to account for that when I use this equation. I could also come up with a quantity, if you are more comfortable with h, I could say h is nearly minus z, and then I could write P as P atmosphere plus rho g h, where h could vary in this direction. So it really depends on the coordinate system that you use. Both are absolutely fine. All right. So our basic aim is to look at the pressure on this submerged object. Now notice that the pressure at different points would be different simply because this height h of the water column is different. Okay. So let me choose a small area. So there is a unit normal, and I could talk about this area dA. This area would have a projection along the x direction and a projection along the z direction. So let me say that this projection, I am going to call this as dAx. Similarly, this projection, I am going to call this as dAz. Okay. And now I could talk about the dF, which is the force acting on this little element here because of the fluid static pressure, and that we know is going to be minus rho g h times dA, where this height is h, as I have shown in the diagram. So if I want to calculate the resultant force, then I would have to integrate it over this entire area, and that would be minus rho g times the integral over the entire surface S times h dA. So I have simply integrated this equation over the entire area. And this Fr is a vector. So it has a component along the x direction and it has a component along the z direction. So I can calculate these individual components. So Fx, for example, would be the force in the x direction. So, notice rho g remains here, and as far as this integral is concerned, now I can say this is dA dot I. And this would become actually rho g times over the area S H d AX. Similarly, I could calculate Fz as rho g over H d Az, where these are the projections that I am talking about, Ax and Az in these pictures. Fr, of course, is given as Fxi plus Fzj. It is a vector. What is the physical interpretation? Rather simple. If I want to calculate the force on this object, what is being said is that if I take an elemental area, then notice H dx is simply, this is H, this is dAz. So, if I want to calculate the force in the vertical direction, I take a small element and calculate what is the force exerted by this prism of water, and simply integrate it over the entire length of this object. So, this then becomes essentially the volume of the prism of fluid on the object. And likewise, when I want to calculate the force in the x direction, then I am going to integrate the volume of the prism of this fluid, which I can see in this projection, and effectively the weight of that. Okay. So, that is how I would calculate the submerged, the force on the submerged object. Now, I could also calculate the point of action of resultant. So, the question that I can ask is that suppose this resultant force was acting through a certain point Fr. What is the location of that point on this object? And the way to do that would be that I can take any point and I can take the moment because of this force, and it should be equal to the moment of the force that I get out of this resultant thing of the distributed load. So, I should be able to, for example, take, let us say, this point O, and then say that equate the moment about point O due to the resultant force and the pressure force, pretty much like what you do for the center of gravity. So, that here would be known as the center of pressure. I would like you to do this as a home assignment. So, please try this for a flat plate. So assume that this object is a flat plate and then try to find out what is the point at which this resultant force acts. It's rather simple. If it's a curved object, then you will have to work a little harder. The last topic that we want to cover in fluid statics is buoyancy. So imagine there is an object, let's say this is the object that I place in the fluid, and I am interested in figuring out what is the buoyant force because of this object. So we have already studied what is the force acting on a submerged object, and now this is a solid object which displaces a certain amount of fluid, and there is a net force on this object because of that. So a 3D object submerged in fluid, and this, let's say, is the atmospheric pressure, and the volume of this object is V. I am going to break this into two parts. So there is an upper surface of this body. So this is the upper surface, and I am going to talk about a lower surface. There is a pressure force that acts on the upper surface, and there is a pressure force that acts on the lower surface. And if I can find the resultant of the force because of these two, then that would be the net force acting on this body, and I would call that as the buoyancy force. So please recall that the pressure is always normal to these surfaces. So first I would like to calculate what is the force on the upper surface. And that's easy to calculate because I would have to take this prism. So this entire fluid rests on the upper surface, and the resultant would be simply, I can calculate because of the volume of the pressure exerted because of the volume of this, and that would be given as rho g, let me call this as Vu. So Vu is the volume of the prism on upper surface of the body. Now I could talk about the pressure force on lower surface, and that would be given as rho g V bottom, and that would be this prism. So this region is the bottom surface. So if I now want to calculate the net force, then you can see that the net force on the lower surface, please note, is going to point out the pressure here is like this, whereas on the upper surface the pressure is somewhat like this. So the net force that I am going to generate is a force rho g, which is V bottom minus V upper, which you will notice is actually rho g times V, which is the volume of the body. So if I look at the difference between the bottom prism and the upper prism, then that is simply the volume of the body. So this is the Archimedes principle. That the buoyancy force experienced by a body is simply the weight of the fluid it displaces. So if I talk about a balloon, so suppose I talk about a balloon, then there is a certain buoyancy force and there is a certain weight. For it to remain static, these two to be in equilibrium, these two should be equal. The weight should be exactly equal to the buoyant force. But then if I fill up it with a gas such that the buoyant force is larger than the weight, then the balloon can rise. So we all know this, but it is good to see that actually coming from the equations of fluid statics. So we'll stop here. I'll assign you some homework problems which you can practice and learn the concept on fluid statics. Thank you.